Okay, you guys, so this is problem number 32 from chapter 8. We have a 9 milliamp independent current source in parallel with a 6K resistor. Before time zero, we have a switch that's open. And there is the other part of the circuit is an inductor with value 62.5 henries. And that is in parallel with a 2.5 microfarad capacitor. And that branch is in parallel with a series connected 3 kilo ohm resistor and negative 15 voltage source, independent voltage source. So what we need to find is the general equation for the inductor current. General steady state equation for the inductor current. And that is basically going to be the final current and the natural response current. So the steps for solving that problem, or all of these types of problems, is to first find the current before time the switching happens. So at time 0 minus, find the steady state current, which is current at time equals infinity. Then, once you have those two, you need to identify the damping. Because whether the current is, or the response is overdamped, underdamped, or critically damped will determine which set of equations you'll be using. Once you determine the type of damping and the type of or the sets of equations you'll be using, you will then solve for the coefficients. And once you know the coefficients, then you have the final answer, which is the general equation for the inductor current. So let's get started. First, pause your video, try all those things on your own, and then when you're ready, play it and compare your answer. So the first thing we have to do is always look at the condition of the circuit before time 0. So before time 0, the switch is open and this portion of the circuit is disconnected from this portion of the circuit. So we have to consider them separately. In this section of the circuit, we've got an independent 9 milliamp source that is basically going in a circle. Like that. 9 milliamps. It's doing that. On this side of the circuit, it looks like this. So in the steady state, the inductors are short, right? And the capacitor is an open, like that. And we're looking for current at the end of the day. So it's going to be in our interest to convert that voltage, which is in series with a 3K, into a current source. So we will do that via source transformation. And source transformation says that this 3K in series with this 15 volt K. So V is equal to IR, so I is equal to V over R, which is 15 or minus 15 really, but it doesn't matter because we will put the sign build the sign into our diagram. So it can just be a 15 over 3K, well that should be 5 milliamps. So we're going to source transform that into a current in parallel with a resistor, like that. And build our sign right into our diagram. 5 milliamps. Now clearly that 5 milliamps is in the opposite direction, so it's going to be negative because we are assigning right here, the diagram has told us which direction is positive. The diagram is saying this direction is positive. So therefore, since it's going in the opposite direction of that makes that the negative current. So now we know that before time 0, we have a 9 milliamp current going in a loop here, And then here on this side of the equation, we have a 5 milliamp source going in a circle just like that. So let's park our initial conditions here. 9 milliamp and negative 5 milliamp. Good. Now we need to consider time at infinity. What does this circuit look like a long time after the switching happens and it's reached its steady state? Well, it looks like this. The independent circuit source or the independent sources are still there. So after a long time, we have something that looks like this, 9 milliamp. Over here, this resistor is still here, 6K. And we have a shorted out inductor. And we have an open capacitor. And we have still this 3K. Actually, we want to put it in terms of current because we are looking for a current. That's the thing of interest. 3K here and $5 milliamps there. What's happening? We have a shorted out branch here, so we've got 9 milliamps going like that. And then here, we've got 5 milliamps doing that. We've got this going in this direction, this going in that direction. That means our final current through the inductor, because that's what we're interested in, is current through the inductor. At time equals infinity, the current through the inductor will be 9 milliamps minus 5 milliamps, and that is 4 milliamps. That's our final current. We need that for our general equation. So, I final of L, I final is 4 milliamps. Okay, that is the first step. Now that we know the initial conditions and the final conditions, we need to look at the damping, because there are three sets of equations associated with each type of damping. So we need to find out which set of equations we're going to use. So the conditions for damping are alpha is equal to, and I can never really remember alpha and omega, so 1 over 2RC, and omega naught is 1 over root LC. If alpha is greater than omega naught, then your circuit is overdamped. If alpha is less than omega naught, then your circuit is critically damped. Underdamped, excuse me. Underdamped. If alpha is equal to omega naught, then you have a critically damped. And all of those will require different equations for solving. So, let's find out which sets of equations we'll be using. So, I'm going to redraw, or put back up here. Actually, I'm going to redraw this circuit right at time when the switching occurs. When the switching happens, we have this is closed, and the inductor is there, and the capacitor is there. And we want to represent this as a 3K resistor with a current that goes like that, and that's 5 milliamps. Just like that. That's right when the circuit closes, or the switch closes. You look like that. So what the heck is R? Is it that R, or is it that R? Well, it's actually going to be the parallel connection between the two of them, because it's the R that's immediately there when the switch closes. And that's going to be 3K in parallel with 6K. So R is actually 6K in parallel with 3K. when you put that into your calculator, you should find out. You should come up with a value of R as 2K. That means alpha is 1 over 2 times 2,000 times 60, times 2.5 micros. Once you do that, I claim that you should arrive at a value for alpha of 100. Okay, now we need to find omega naught to see which one is the greater number. Well, that is 1 over the square root of 62.5 times 2.5 microns. And I claim that if you put that into your calculator, you should come up with 80. So in the case of this particular circuit, we have alpha is greater than omega naught. Therefore, this is an overdamped response. And so we will use our equations for an overdamped system to find the final step equation. And those equations are that equation, the general equation will be IL of T is equal to I final plus A1 prime E1 S1 T, just E, plus A2 prime E to the S2 of T. That is your final equation, and the coefficients, so we need to find the coefficients. Well, first we need to find the S, right? So S12 is negative alpha plus minus the square root of alpha squared minus omega naught squared. That is S12 for the exponentials of the general equation, and for the coefficient equations, we have di dt exactly at 0. That is equal to A1 S1 plus A2 S2. So this gives us two equations, two unknowns, and actually this should be I0. This is a coefficient one. So the current at time 0 through the inductor is equal to the final current. And okay, I have to always double check my work because I find that I make mistakes on videos if I rush and it's just a stupid plus or minus mistake. So, but then it creates a lot of, for example, primes. It creates a lot of confusion for people who are trying to learn it. So, just want to slow down a little bit. All right, so now that we have everything, let's take a look at the S's. We had the alpha was 100, so it's going to be minus 100, and we've already figured out omega naught and alpha, so this is going to be 100 squared minus 80 squared. And I claim that you should come up with S1 is equal to negative 40, and S2 is equal to, I don't have a lot of board space here, sorry about that. S1 is equal to negative 40, and S2 is equal to negative 160. So that's a couple of huge chunks off of our final equation. Now we need to figure out what the heck our coefficients are. So initial current through the inductor is equal to the final current. So what is the initial current through the inductor? Remember, when the switch was open, this was a short, this was an open, and this was just 5 milliamp going through that and shorted out inductor. Therefore, right at time when the time switches, remember that the inductor cannot change current instantaneously. Therefore, that negative 5 milliamps that was looping through the inductor when it was shorted is still looping through the inductor. So therefore, this is negative 5 milliamps. And the negative comes from the fact that the diagram defines this direction as the positive. So if the inductor is going in the opposite direction, then the passive sign convention says that that's a negative current. The final current we said was 4 milliamps. And that is plus a 1. At time 0, the e goes away. The e to the 0 power is 0, is 1. Plus a 2 prime, e to the 0 power is 1. So then the first equation that we have that we need to solve this is a1 prime plus a2 prime is equal to negative 9 milliamps. That's equation number 1. This can go away. So we have one equation and 2 unknowns. Let's rewrite this up here. Okay. Equation 2 that we need for solving this is di dt, the change in current at time 0 of the inductor current, because that is what we're interested in, is equal to S1 times A1 prime, S2 times A2 prime. So S1 is the plus, so it's going to be alpha plus that stuff, and that is going to be negative 40 A1 prime. S2 is the minus, so it's going to be the alpha minus all that junk, and that's going to be the negative 160, and that's equal to di dt, change in current through the inductor at time 0. But the property of the inductor is that it cannot change current instantaneously. It can change voltage, and does. It changes voltage wildly in order to maintain that constant current when the switching happens. So because the inductor cannot change current instantaneously when switching happens, the di dt is 0. And we derive that strictly through understanding the properties of an inductor. So that is equal to 0 amps. This is 160 A2 prime. That's our second equation. Negative 40 A1 prime minus 160 A2 prime, that's equal to 0. I claim that, well, you know what? I don't have to claim that. We can solve that. So let's do that from the old school way, keeping that up there. All right, so the old school way is by adding, if I multiply this through by positive 40, then that's going to give me plus 40 A1 prime plus 40 A2 prime, A2 prime, that's equal to negative 360 milliamps. Now I can add these equations together, and that will give me negative 120 A2 prime is equal to negative 360, and therefore A2 prime is equal to, that looks an awful lot like 3. But I'm notorious for being completely inept at doing basic math in my head. So I'm not even going to try. 360. You have no idea how many dumb points I've missed on exams just because I can't do basic things like negative 360 divided by negative 120. That is 3. Put that back in here. So That means A1 prime plus 3 is equal to minus 9. Therefore, A1 prime must equal minus 12. Now we have all the pieces to put back into our general equation. So, our general equation, remember, is okay. The general equation for final general equation for inductor current through this circuit is I final, the current through the inductor in its steady state, plus A1 prime e to the minus S1t plus A2 prime e to the minus S2t. We have all pieces, so the answer to this problem is IL of t is equal to 4 plus minus 12 a to the negative 40 t plus 3 e to the minus 160 t milliamps. And that is the answer I came up with. So, I'm definitely guilty of making mistakes. If you see any, let me know. But I try to be super slow and try not to make like dumb little plus minus mistakes and such. So that is what Spice tells me is the answer to this circuit. All right, good luck, and be sure to share this video if you received help from it. And also please like the Facebook page, because we kind of need to have people find us in order for this channel to be something more than me doing all the videos, because as much as I want to, I just can't do every single problem in the fashion, the type of time that I want to. So please help by liking the Facebook page and sharing the video. Thanks.